Imagine a train that has no wheels, makes almost no noise, and flies through the air at over 600 kilometers per hour. This is not science fiction. It is the reality of magnetic levitation or maglev technology. Today's fastest bullet trains are marvels of engineering, but they face a fundamental physical limit. Because they rely on steel wheels on steel rails, they hit a speed ceiling around 350 kilometers per hour. That limit is caused by friction. When two steel surfaces press together at high speeds, they lock and slide. This friction creates intense heat, mechanical wear, and consumes massive amounts of motor energy just to overcome. To go faster, we have to eliminate the wheels entirely. That is where maglev comes in. By using powerful electromagnets, maglev trains lift off the ground, floating on a cushion of air and erasing mechanical friction. Think of it like two toy-bar magnets. If you push the two matching north poles together, they will push apart with invisible force. Maglev trains use this exact repelling force to float above the tracks. Engineers have developed two primary ways to make a train float. The German system uses magnetic attraction to pull the train up, while the Japanese system uses magnetic repulsion to push the train up. The German method is called electromagnetic suspension. Electromagnets on the train's undercarriage wrap around the steel diode track. When turned on, they pull upward toward the rail, lifting the train. This attractive lift is like walking a tightrope. The gap between train and track is only 15 millimeters. Active computers must monitor and adjust the magnets thousands of times per second to prevent them from crashing. The Japanese method is called electrodynamic suspension. Instead of pulling up, it uses repulsive force. Powerful magnets on the train push against magnets in the track walls, pushing the train upward into a stable float. To push a massive train upward, it relies on superconducting magnets. These specialized magnets generate incredibly intense magnetic fields, allowing the train to float much higher, about 100 millimeters above the track. Superconductivity requires extreme cold. Coils on the train are cooled with liquid helium to -269 degrees Celsius. At this temperature, electrical resistance vanishes, keeping the magnets powered continuously. Because Earth's repulsion only builds up as the train moves faster, it cannot float at a standstill. The train starts on rubber wheels, rolling like an airplane until it hits 150 kilometers per hour. How does a floating train move without wheels or a jet engine? The answer is in the track. The guided walls are embedded with electromagnets that act as a giant stretched-out electric motor. Think of it like surfing. The track generates a moving wave of magnetic fields. The train's magnets lock onto this wave, pulling the train forward like a surfer riding an ocean swell at high speeds. This magnetic wave works through push-pull mechanics. Track magnets ahead of the train pull its front magnets forward, while track magnets behind push its rear forward, creating incredibly smooth and rapid acceleration. To slow down, the track simply reverses the direction of the moving magnetic wave. This acts as a powerful brake without any physical friction. Best of all, it feeds electricity back into the power grid. With friction gone, a maglev train's only opponent is wind resistance. Air drag increases exponentially at high speeds, which is why maglev trains are designed with long aerodynamic needle-shaped noses to cut through the air. Conventional trains struggle to climb steep hills because steel wheels slip on steel tracks. Maglev trains have no wheels, allowing them to easily climb inclines of up to 10% without losing traction. Since nothing rubs together during transit, maglev systems experience virtually zero mechanical wear. The vehicles and guideways last for decades, drastically lowering long-term maintenance costs compared to standard high-speed rail. However, maglev infrastructure is expensive to build. The special concrete guideways must be constructed from scratch, but because operating costs are so low, the system can pay for itself over time on busy routes. The world's first commercial high-speed maglev operates in Shanghai, China. It connects the airport to the city center, hitting speeds of 430 km per hour and covering 30 kilometers in just 8 minutes. Japan is currently building the True Shinkansen, a massive maglev line designed to link Tokyo and Osaka at 500 km per hour. Once completed, it will cut the travel time down to 67 minutes. High-speed maglevs face unique challenges in tunnels. As the train enters at high speed, it pushes air forward like a piston in a syringe. Engineers build special hoods at tunnel entrances to quiet the resulting sonic booms. Moving a massive train magnetically requires high-peak electrical power. Maglev tracks draw heavy current from local substations, especially during acceleration, requiring robust integration with the local electrical grid. To go even faster, engineers want to remove the final barrier air. By running a maglev train inside a sealed tube and vacuuming out the air, we can eliminate aerodynamic drag entirely. Inside an airless vacuum tube, a maglev train could exceed 1,000 km per hour. This matches the speed of commercial passenger jets, allowing us to travel between major cities in a fraction of the time. Maglev trains are incredibly safe. Because the train wraps around or sits deeply inside the U-shaped guiding walls, it is mechanically locked to the track. A conventional derailment is physically impossible. In earthquake-prone regions like Japan, Maglev's large levitation gap provides safety. If the ground shifts, sensors instantly cut power, allowing the train to slide safely to a halt on its landing gear. Maglev trains are much quieter than standard trains. Without wheels screeching or engines roaring, the only sound is the rush of wind. This makes them ideal for running close to residential neighborhoods. Elevated on concrete pillars, maglev tracks have a tiny ground footprint. Farms, roads, and wildlife can pass freely underneath, minimizing disruption to communities and reducing the cost of land acquisition. By slashing travel times, maglev links distant cities into single, accessible commuter zones. It offers a faster, cleaner alternative to short-haul airline flights, helping travelers reclaim hours of their day. Building superconducting magnets requires rare metals like niobium and titanium. Sourcing these materials involves specialized global supply chains, contributing to the high upfront capital cost of maglev systems. The liquid helium used to freeze the magnets is a non-renewable resource. Rising helium prices and supply shortages have pushed engineers to search for alternative cooling methods for future trains. The solution lies in high-temperature superconductors. These new materials can achieve superconductivity using liquid nitrogen instead of helium. Liquid nitrogen is cheap and abundant, drastically lowering cooling costs. The biggest barrier to maglev adoption is upfront cost. Because maglev trains cannot run on existing standard train tracks, entire new networks must be built from the ground up, requiring massive government investment. Maglev is most feasible along heavily crowded transit corridors, such as Tokyo, Osaka, or Boston, Washington. These high-volume routes justify the construction cost by saving millions of passenger hours. In summary, German EMSA traction keeps a tight 15mm gap using active computer controls, while Japanese ETS repulsion uses frozen superconductors to float 100mm high. Both represent the peak of transit engineering. The next time you see a train, you will know the incredible physics that could soon make it float. Thank you for watching. At Laymans Field, we believe in sharing knowledge for everyone.